everyone? What's up, everyone? It's your boy. It's your boy. JOHABRAHAM. Let's go. I just went to get the coffee. And I thought, why not just keep the stream running? We got some chat. Devoto did. Hi. Hey, yo, what's up? Appreciate Devoto did for checking out the stream. Average Sandstand streaming right now, twin. Hell yeah, twin. Okay. How long was the stream though? How long did it take me to get the cup of coffee? I gotta see this. The stream has been going on for 5 minutes. Yo. It takes me 5 minutes to get a cup of coffee? That's not good. That's not good. That's never good. The mic is working, right? Yep. So will they not there? Ficaro. Will they react with water? So tellurium, I was looking into tellurium. Why tellurium fluoride does react with water? Because the MCN for period tellurium is part of 6, right? Tellurium, yeah, it's 3. Oh wait, 3, 4, 5, 5, 5. Period 5 and 6 has maximum coordination number 8. So 2 more ligands are possible. Also, das macht Sinn, oder was? Oder was? Oder was? Bonds are polarized / replaceable. TEF6 satisfies both. Okay, I need more explanation on. Okay. Wait, how do I know that? Wait, how do I know that the bonds are replace? Oh, bro, shut the fuck up. I don't need this thing. Does the central atom has room for attack? First check for MCN. If MCN is already full, Mm, then bond replacement is irrelevant because water can't even get started. It's the central atoms highly strongly electrophilic. Look at Z squared by R. And XP, high value means central atom pulls electron density strongly, water is attracted. Hydrolysis become more likely. Okay. Okay. Shit, I forgot the timer. 1 hour, right? 1 hour. 1 hour. 15 minutes. 30 minutes. 45 minutes. 30 minutes. Just did not hear me. I think I could close the window. I just want the air to refresh. XP greater than 1. Okay. If these values are given, what's the threshold? Like, how do I know if which from which value onwards they are electrophilic, etc. Yep, that's what I was looking for. Charge density, Z squared by R equals greater than 1.8. Strongly polarizing electrophile. And MCN for TE equals 8 period 5. Therefore, water has tendency to attack TE, and there's more space. TE has more space to accommodate ligands. XP less than 1.8. Low polarizing ability. XP greater than 1.8. Strong polarizing ability or electrophilic behavior. Atmosphere chemistry. CFCs, freezing agents, stays in atmosphere for 40 years. SF6 can light short, short wavelength, high energy. Wavelength or frequency? That's wavelength, right? SF6, 3,200 years, okay. Atmosphere chemistry. Atmospheric pollutants. CFC, SF6. Chemically inert, so it accumulates, okay? UV breaks stable molecules, release reactive species. These species destroy ozone. Other pollutants include CO2, CH4, NO2, N2O. Radical chain reaction, okay? The reaction, but I can see it and redraw it So let me know if there's anything. Radical chain reaction. RCl. Yes, for exam purposes only you need the core radical chain mechanism logic, not every arrow pushing detail. What you must understand: CFC radical chain, CFC are broken by UV light, initiation, UV breaks bond, forms radical. Key idea: UV creates a radical chlorine, propagation chain reaction step. This is the most important part. Key insight: chlorine is regenerated. Chloroxy radical. What's the exact name for this radical? There is no. So it is not consumed. One radical destroys many ozone molecules. Net effect: O3 to O2 ozone depletion. Chlorine acts as a catalyst, not a reactant. Point. So let me write the reaction. Generic CFC. RCl. Homolysis. Electrons are equally shared, or electron pair is shared as electron. What's the term? It's a third. There's no terms. R plus Cl minus Cl. The radicals. Then the chlorine radical reacts with the ozone. And forms a chloroxy radical. This comes in contact with ozone. Let me draw ozone. Ozone. The negative charge goes here, forms a bond. But still the oxygen has a radical. It's just one bond. Okay. The 2 is used for, it already has 2 lone pairs, but it still has still has 1 electron left. Yep. CO chloroxy radical plus oxygen Weak bonds unstable. UV chlorine radical plus oxygen. Oh, okay. Okay. So that's that. And when so both given the same radical electron, form bonds. Damn, 15 minutes, god damn it. So that's the, is there, no, weak bonds. Light results in Cl radical, 2 Cl radical plus O2 chain reaction. Similar reactions with SF6 with similar reactions for SF6 but with F radicals. Acid-base reaction, HCOH, what's this? Acetic acid? All species are colorless. Need to use phenolphthalein indicator. Okay. Speciation diagram. Predominance. Oh, okay. There we go. This one, they asked me this on the exam, I believe. It's mainly about. Okay, while it explains, let me do this. So we start with RF, right? Why is it Cl though? RCl is a generic CFC. What the fuck? I don't get it. It's chlorofluorocarbons. Why? Wait. I did not notice that. Wait. Wait, before we proceed. Wait. Before you explain the acid base, I'm having doubts on the CFC, but then for the chain reaction, UDRCl was used. I did not see any Cl in CFC. Where's the mouse, bro? CFC do contain chlorine. That's a key point you're missing. What is CFC actually? Chlorofluorocarbon. General form is CClXF4 minus X. Oh, what the fuck? I thought it was CFC was C. Chlorofluorocarbon. General formula. CClXF4 minus X. Okay. Okay, now RCl generic form, CFC, homolysis, right? Homolysis radical plus Cl radical. And it results in so we got two Cl radicals again plus oxygen. That's how it's a fucking chain reaction, mate. This is a weak acid, strong base titration curve. Acetic acid plus NaOH. The page is describing how chemical species and pH change as NaOH is added. Acid equals acetic acid, weak acid, NaOH, strong base product equals acetate. Initial region 0 milliliter NaOH, only acetic acid and water. What happens? Partial dissociation only. Affects low pH but not extremely low because of weak acid. Okay. Buffer region 0 to 50 milliliters. Now both species exist, acid and conjugate base. What happens? Added NaOH converts acid to conjugate base. So mixture becomes acid plus base pair. Buffer system. Key property resist pH change. Half equivalence point. Equivalence point. Get some water. I'm gonna need some water. Just a minute. No way. How does it even work? I don't know. acid base reaction. Weak acid plus strong base. ACOH plus, ow, ACO and A plus. Fuck. So it's like 30 more minutes plus H2O. Zero milliliter NaOH. Only acetic acid and water. What happens? Partial dissociation only. Affects low pH, but not extremely low because weak acid. Buffer region 0 to 50 milliliter. Half equivalence point. pH equals pKa. All species are colorless. Need to use phenolphthalein indicator. But what does this has to do with inorganic chemistry? Okay. Can you explain what does this has to do with inorganic chemistry? Or is this actually part of inorganic? And I just came across this in inorganic. I thought it was chemical calculation. This is absolutely chemistry. What? That belongs in organic, of course. The reason behind concluded is one of the main themes of inorganic chemistry, how it connects to what you're studying. You already spent a lot of time on hydration of cations, hydrolysis, Lewis acid, Ronson acid. Those are all acid-based concepts. For example, act as an acid because it can donate the proton. That's exactly acid-based chemistry. Why are they showing acetic acid? Acetic acid is a familiar example that everyone knows. The lecturer is probably using it to teach pH, pKa before applying the same ideas to inorganic species. Okay. Acetic acid example itself is probably not the main point. The important ideas are Ka, pKa, buffer region, half equivalence point, acid-base equilibria. Okay, I gotta do this again. Okay, then explain this to me, because I kinda forgot everything I learned in Genochem. Also, there's a formula that's not available in the it's pH. Fuck. Let's rebuild this from the ground up. What is happening in this titration? You start with 50 milliliters of 0.1 acetic acid. Reaction, the OH from NaOH consumes acetic acid and converts it to acetate. 50 milliliters of 0.1. Okay, that's where you start. Okay, I get that one. I get that. That was cocaine. I wish. I wish that was cocaine. It's a joke. It's a joke. YouTube is a joke. Please, come on. Come on, YouTube. Come on. What are we doing, YouTube? What, YouTube, come on. The OH from NaOH consumes acetic acid, then converts it to acetate. Before adding NaOH, volume of NaOH 0 milliliters, solution mostly acetic hydroxide. How? Oh, that's where. Oh, okay. It's not like alcohol. My mind was going, what? Why is it OH? It's alcohol. No, it's acetic acid. Gang. Yep. Part 1 or before adding NaOH base. Solution is acidic as only acetic acid is present. Buffer region, stage 2. Here we start with adding NaOH. Suppose you add 10 milliliters, some acetic acid reacts. Now you have acetic acid left over, and the reaction starts to proceed, and we should have both ACOH ones that did not react with OH from NaOH, ACO minus that did react buffer. Mixture of weak acid and its conjugate base. Here weak acid is the buffer resists sudden pH change. Resist that's Henderson-Hasselbalch equation. Henderson-Hasselbalch equation used only in buffer region. pH equals pKa plus log conjugate base divided by acid ACO minus if there is more acetate half equivalence occurs at 25 milliliters of half of the acid has reacted, half remains, therefore and log 1 equals 0, so pH equals pKa. That's where your notes say equivalence point at 50 milliliter in OH. All the ACOH has reacted. Now you have ACO minus, but now acetate, but almost no ACOH. Now acetate behaves as a weak base. It produces OH minus. I can't see the acetate ion, brother. I can't see it. Fast, 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 fast. Why won't you work? It's still not showing. "45 minutes is over. God damn, son. God damn." I'm gonna start with UV spectroscopy, right? Fuck, I forgot what PKE here is. I kind of forgot what exactly pKa is, and also the pH. Like what I remember, concentration of H plus ions in the solution. Fuck. I can see the equation where acetate now acts as base. Also at equivalence point, all the acetic acid is now converted to acetate ion, or the so that itself means it's a base. Yeah. uh, when now OH when the amount mm-hmm. What is pH? You remembered correctly. Shut the fuck up. Don't say shit like that. Oh, you're really good at remembering things, bro. Those are basic stuff. Meaning high H3O plus, low pH, acidic, low H3O plus, high pH, basic. pK. First remember Ka equals H plus. So conjugate base with conjugate acid divided by the compound or acid's concentration. Negative logarithm of pKa. What does pKa mean physically? Think of pKa as how willing is the acid to give away H plus. Lower pKa, stronger acid gives H plus more easily. Higher pKa, weaker acid holds on to the H plus more strongly. Okay. I think I need that pKa. I need to understand the pKa, because if I did not understand that, I think it's a waste of time. Acid pKa. Okay, why pH equals pKa at half equivalence? At half equivalence, insert into the Anderson-Hasselbalch equation. So at pKa, how willing is the acid to give away H plus? So at equivalence or half equivalence point, it's just mathematics. Again, at half equivalence point, uh, negative logarithm of H plus equals negative logarithm of Ka, which is again how is, wait, it's negative. Yeah, both are negative. So Ka equals concentration of H3O plus, or H plus ACO divided by, say, that means ACO minus and ACOH. Conjugate base and initial acid concentration are equal. Fuck, it's a nomenclature. Ooh. Just a minute. Just a minute. Conde. Partiro. pH equals negative log of H plus or negative log of H3O plus. pKa equals negative log of Ka. Now Ka equals H plus A minus divided by HA. pKa is basically a term to show how willing is the acid to give away H plus. Strong acid easily give away H plus. Weak acid hardly give away H plus. At half equivalence point, the concentration of acid and the concentration of the conjugate base is equal. Aha. At half equivalence point, concentration of acid equals concentration of conjugate base. pH equals pKa. Henderson Hasselblad equation, part of Henderson Hasselblad equation. Hasselblad equation. Hasselblad. Blah. Acetic acid loses an H plus and become acetate. Acetate. Conjugate base. So acetate, think of it like this. AC always says I give away my proton. I would like to take that proton back. Therefore, ACO minus plus H2O equals acetic acid plus. Acetate takes H plus from water. Water loses H plus. So we got acetic acid and OH minus. Solution contains lots of acetic acid. So immediately the OH gets consumed. With this as an accumulate. Think of it like this. You pour water into a sponge. Sponge absorbs it immediately. You don't see the puddle. Okay, what changes at the equivalence point? Acetic acid still exists. Any OH added gets eaten by acetic acid. After equivalence, no ACOH left. Now there's nothing left to consume. OH minus, only major species is ACO minus, which reacts with water. Now produces... it's interesting. So it goes from conjugate base to acid again. That's weird. But you know what? It's 1 hour. Change the subject. Peace out, YouTube.